Thank you, Jeremy, for that typically embarrassingly generous introduction. Welcome, everyone. It's wonderful to see so many old friends here and so many interesting people that I haven't met before who are on their way to becoming new friends. So welcome, everybody, to Cambridge and to Trinity. A few of you, I'm afraid, have seen most of this talk before, so apologies to those people. And well, I should also say that some of it will seem excessively elementary to you. This is partly a reflection of the fact that parts of it were written for other audiences, and partly to do with the fact that I'm incapable of thinking about things except in very simple ways. And so this is my attempt to get things clear for myself. Well, let's start with a little bit of history. Here's a crude representation of a typical EPR Bell experiment. What Einstein, Podolsky, and Rosen used this kind of experiment to argue in 1935 was that quantum mechanics must be incomplete. That is, that there must be further elements, what are these days called hidden variables, which are not part of the orthodox quantum description, but which they argued and needed to account for the kind of perfect correlations that we find in these cases. Now, as their argument made quite explicit, they were assuming a principle they called locality. It's a kind of no action at a distance principle. So the assumption that choices made by Alice don't affect the results of measurements made by Bob over here, and vice versa. And that at the time seemed uncontroversial. As Schrödinger put it in the same year, measurements on separated systems cannot directly influence each other. That would be magic. Okay, but as we all know, 50 years ago this year, Bell showed an extraordinary result, which most people have interpreted to mean that, indeed, magic happens in that sense. So Bell showed that, or is interpreted as having shown that no local hidden variable theory is compatible with quantum mechanics, with the quantum mechanical predictions in these sorts of cases. Now, as many of you will know, there's still a very lively debate about what precisely Bell showed. And I'm not going to get into that debate, but I just want to give you a common reading of it, a common message that people take from Bell's results, and that's that the quantum world is unavoidably non-local, so that in some subtle sense there is action at a distance from Alice to Bob and Bob to Alice in these kinds of experiments. Here's a quotation from some people who read Bell's theorem in this way. This is from an article that some of you may know in Scientific American a few years ago. David Albert and Rivka Galchen say, quantum mechanics has upended many an intuition, but none deeper than locality. And this particular upending carries with it a threat as yet unresolved to special relativity, a foundation stone of our 21st century physics. Okay, so that's Bell, 1964. But going back again about 10 years or so, we find something that I think people haven't paid enough attention to. In assuming locality, as I said, Einstein, Podolsky, and Rosen had in effect relied on the principle of no action at a distance. But in the late 40s, a Parisian graduate student, shown here with his advisor, Louis de Broglie, spotted a loophole. He saw that Alice's choice could affect Bob's particle and vice versa without action at distance if the effect followed a zigzag path via the past. This graduate student was Olivier Costa de Beauregard, shown here much later in his life. Shown here again a couple of years before his death with a young admirer. And here's a diagram from one of his papers paper from the 1970s, I think, with his caption. It says, this is a space-time diagram of the Einstein paradox. The correlation between L and N is tied through C in their common past via the Feynman-style zigzag made of the time-like vectors CL and CN. I think it's of some historic interest that Costa de Beauregard is describing it as a Feynman-like zigzag. When I met him on this occasion in 2005, I asked him when he'd first had the idea. I knew the first publication on it was in 1953. And he said, oh, back in the late 40s when I was a student of De Broy's, but he wouldn't let me publish it at the time because he thought it was too crazy. And then after Feynman's work came out with the Feynman zigzags, and positrons being treated as electrons going backwards in time, that kind of thing, De Broy relented and said, look, you know, there's this clever young American publishing these sort of crazy ideas, perhaps you should publish yours too. Okay, but one interesting thing about this, which I didn't realize when I first came across this stuff. It seems that Costa de Beauregard thought of this, when he first proposed it, as an objection to the EPR argument, because he thought, well, it undermines the case for the assumption of locality. It shows how something that happens over here could affect something that happens over here without action distance, because the effect goes this way. So he saw it as an anti-Einstein point. I think he saw it as a point which could be used on Bohr's side of the argument between Einstein and Bohr. But it can't undermine the EPR conclusion because the zigzag is not there in standard quantum mechanics. So if we want to put it in, we're accepting with Einstein that quantum mechanics is incomplete. So the zigzag needs some sort of hidden variables, in other words. So I think Costa de Beauregard was in this respect a little bit mistaken about what the significance of his own idea is if we take it seriously. And certainly to me, it's always seemed that the attraction of this idea, what we now often call retrocausality, is associated with its implications for, generally speaking, the hidden variables approach to quantum mechanics. Now, and I think the really interesting thing about Costa de Beauregard's idea is one whose significance can't possibly have been accessible to him at the time because it depends on Bell's results. So the real attraction of it is that it may be the way to save locality in the face of Bell's theorem. And this is because Bell's argument simply assumes that, say, Alice's choice of measurement settings doesn't influence the prior state of the photon, and correspondingly for Bob. So in effect, Bell's argument is assuming that there's no such thing as the Parisian zigzag that Costa de Beauregard wanted to postulate. And the Bell correlations are easy to explain in principle if we do allow we do allow Alice's measurement choices to have an influence on the state of the particle before it reaches her measurement device. So in other words, if we allow for the Parisian zigzag. And so in this way, at least in principle, we can save locality. That is, we can do without action distance, precisely the thing that Costa de Beauregard was recommending, and the tension with relativity vanishes. Well, in the light of that, I think, I mean, none of that is particularly deep. It's an interesting question as to why the Parisian zigzag isn't more popular. Here's some indication of Bell's own answer to that question. This is an extract from my one and only letter from Bell, sent, as you see, on the 8th of June, 1988. Fortunately, a few years before the widespread adoption of email, which is why I have this wonderful handwritten letter from Bell. And Bell says, I have not myself been able to make any sense of the notion of backward causation. When I try to think of it, I lapse quickly into fatalism. And this was a tendency that Bell evidently shared with many other people. Many people have lapsed in the same direction, which is really why our conference is called Free Will and Retrocausality. Many people have thought that issues of free will are entangled with the questions that come up if we try to investigate what I'm calling the Parisian zigzag. I'm not going to talk directly about issues of free will in this talk, but as you can see by looking at the conference program, it's certainly on the agenda here, and we'll have other opportunities to discuss it. Other common responses that you get if you go around saying the kinds of things I've been saying, why aren't you thinking about this option? Well, people say, show me a model. It's a very sensible response. Another thing that people say is that retrocausality would imply retrosignaling, and that would lead to paradoxes, something like the standard sorts of paradoxes thought to be associated with time travel. Now, later in the talk, I want to show that we can do something to meet those objections. Particularly, I want to say something about the second one. I think there's a simple argument which shows how we could have the kind of retrocausality that we need to exploit the Parisian zigzag without any danger of retrosignaling. But first, I want to give you something different. I want to give you what I think is a new argument for retrocausality in quantum mechanics, and an argument which could in principle have been discovered long before the EPR argument, because it doesn't depend on anything as complicated as the sort of two-particle experiment involved in the EPR argument. As far as I know, it hasn't been noticed before, but I think there's a sense in which that's a kind of historical accident, and if it had been spotted, the fact that retrocausality also provides an attractive response to Bell's theorem might have seemed much less controversial. Okay, so the next and sort of central section of the talk is the presentation of this new argument as I'm thinking of it. And it relies on a comparison between a classical and a quantum treatment of a simple polarization experiment. So let's do the classical case first. So what we've got here is a beam of polarized light, classical light. This is a polarizing crystal which splits such a beam into two. There's the transmission part of it which continues through the crystal unimpeded, and the portion which gets reflected off in this direction. The crystal has an angle setting, the beam has a polarization angle, and there's this classical law, Marlas's law, which tells us the intensity of the two output beams, the transmission beam and the reflection beam, in terms of the difference between these two angles, tau, the polarization angle of the beam, and sigma r, the polarization, the angle of the setting angle of the polarizing crystal. Okay, and this is what you could think of as the time reverse case of this, where you're using one of these crystals to combine two polarized beams into one. Of course, it's a little bit tricky to do in practice because you have to get the phases exactly right so that the beams interfere in such a way that you just get one output beam. But in principle, this is time symmetric theory, so in principle this is possible. What we're going to do now, what's in effect the same law, Marlas's law, applies to the intensities that you need for the input beams here in order to get this output beam with this polarization. Okay, so now all we're going to do is to put those two cases together in this simple apparatus where light is fed into this crystal. We have a beam of polarizing light crossing the gap, and then it's split again on this side. A couple of comments about that. One is that it's very natural here to think of the polarization of the beam as a local mechanism, that is, as the piece of reality which can be used to convey a causal influence, or say a signal from this side to this side. So if we had this piece of apparatus, there's lots of ways in which we can use it to do things, to act as a kind of control device, so that changes we make over here will produce changes over here and thereby control something or other, or be decoded as a message. And if we're using it like that, then all our intuitions which tell us that causal processes require mechanisms will lead us to focus on polarization as the relevant mechanism in this case, because it can be set up so that polarization is the thing that we're changing when we change something over here in order to do something over here. So that's I'm just saying that to sort of pump your realist intuitions, and that'll become a bit more important in the quantum case. And what we're going to be thinking about is what we can wiggle or change if the only things we control are the polarization angles, sigma L, or the angles of the crystals, sigma L and sigma R on the right here. So this little line symbolizes wiggling. Here's us. We're going to be acting as free agents, wiggling either that or that, and thinking about what else we can control. That's what's going on. And there's going to be nothing surprising, really. Okay, so first of all, let's consider the case where we just control the angle of the left-hand polarizer. And you see I've added this knob to the diagram so that we can actually think in a more realistic way about reaching in and making a setting. Okay, so suppose that's the only thing we control. The input beams, the beams of light coming in on these two channels here, they're under the control of a character I'll call the demon of the left. Here's the demon of the left, looking suitably demonic. Question: in these circumstances where this is the only thing we can control, can we control the polarization of this beam? Or does the demon control it, or is control somehow shared between us and the demon? It turns out the demon has it all. That is, if the demon knows what angle we've chosen, which you can see simply by looking at the knob here, then he can produce a beam with any polarization he likes, given that angle. And one easy way to see that is to see what intensities nature would produce with the same polarization setting on this side. And from the time symmetry, it then follows that they're the inputs the demon needs to provide on the other side. So whatever changes we make here, the demon can counteract them, so that there's no change in the polarization of the beam. You see, here I am making changes to the polarizer setting on the left. So you can see the polarization isn't changing. That's because the demon is making changes up here. Okay, and not particularly surprising. Now let's think about the corresponding case on the right here, where we're just controlling this polarizer setting. In this case, we'll have nature as normal controlling the intensities on the two outputs here. Nature in the form of this rather large cat is a sort of hint of the quantum case that's to come. Again, when we make changes here to the setting of that knob, do we make changes to the polarization of the beam there? Well, you might say, well, if it weren't this conference, you might say, well, no, of course not. That would be retrocausality. And in the classical case, that's the right answer. So, you know, here I am making changes here. Nature makes changes to these intensities, these two output beams. Nothing changes here. So again, this is just what you would expect. So there's no retrocausality in this classical case. Okay. Now the interesting thing is that the quantum case is different, at least under certain assumptions. I'm not going to try and make those assumptions explicit. So once again, we have the right-hand side of the apparatus in the quantum case, where the difference is that we've replaced the beam with a single photon source. We have a quantum version of Marlus's law, which replaces the intensities with probabilities. Again, If we're careful, we can have the time reverse version. In this case, it's if we want to talk about probabilities in this case, we have to be a little bit careful about what we mean. That's, if anybody wants to discuss that, we could discuss it in Q&A, but I think if we're careful, we can make sense of this time reversed law in this case too. Okay, and here's the apparatus we get if we put the two pieces together. Again, I want to just point out that since we can, at least in the case where we're controlling the inputs here, we can use this device, say, to signal or to control some mechanism over here on the right-hand side. And we can do that by varying the polarization of the photons going through it. Again, it's natural to think of the polarization, but I'll explain later why I've now got a subscript on this, tau L. It's natural to think of that as a piece of reality, a causal mechanism, a beable in Bell's terms, which connects changes on the left to changes on the right. But since I want to be explicit about the assumptions, I'm going to give that assumption a name. I'm going to call it realism. So realism is the assumption that there's a beable here. There's some piece of reality between the experiments which is influenced in the right sort of way by what we do over here. Okay, and again we're going to be thinking about what we can control if the only places we have control in the apparatus are at the measurement settings of the two polarizers. Okay, so as in the classical case, assume that we control the left-hand polarizer, but not the input photons. Here's the demon controlling those. Can we control this beable tau L? And in the classical case, the answer was no, that the demon had complete control, as long as the demon knew what setting we'd chosen, of course. In this case, the answer is different. So long as we make one further assumption, namely that the demon has to put the photon on one channel or the other, the demon can't spread the photon as a superposition between the two channels. So long as we make that assumption, I'll call it the discreteness assumption, then it turns out that we do have some control over the polarization in this case. Namely, that if we choose a setting sigma L here, the only two possibilities for the polarization are for tau L to equal sigma L, in the case in which the demon sends the photon in this way, or for tau L to equal sigma L plus pi on 2, in the case in which the demon sends the photon in that way. So, although we can't control the polarization completely, we can restrict it to just two possibilities, which is a lot more control than we had in the classical case. It's easy to see where that's coming from. It's coming from the fact that whereas we've still got an infinite range of options to choose from here, the demon now only has two options to choose from. So it just doesn't have enough options to counteract all the changes that we can make at this point. So it's the discreteness thing which is doing the crucial work here.
So if we knew which choice the demon had made, then there wouldn't be those two choices.
Well, yeah. If we know which choice the demon has made, then we can get it exactly. Yeah. What I'm interested in is the case where we don't know in advance the choice of the demon, and the reason for that is because I want the behavior of the demon over here to be as much as possible like the behavior of the nature over here, and it's that symmetry that I'm now going to appeal to. So what we've shown in effect is that there's what we might call a degree of input-independent control on the left-hand side that we just get if we have control of the polarizer setting here. And that's new as a result of discreteness. I mean, of course, we could get it in the classical apparatus too if we impose discreteness on that apparatus. So if we just had a classical case and restricted the demon to the options of firing a laser beam through one channel or firing a laser beam through the other channel, then of course we'd get it in that case too. Okay, oh, and this is just so we can visualize this control. So I've here represented the polarization by this cross, where the cross represents, as it were, we don't know if the angle is this one or the one at 90 degrees to it. And now you can see how when I move the knob, I'm changing this property of the photon, which, given the assumption I call realism, is, so we're changing something in the world between the two polarizers. Okay, stop doing that and move on to the right-hand case.
Here, I think you have a question.
Oh.
Can I just ask a clarifying question?
Yeah, sure.
So, if the photon is definitely in beam 0 or 1 on the left, then is it true that some of the time the photon just doesn't go between the left and the right?
Yeah. Sorry. There's it's a good question, Faye. I mean, there's to set this up completely properly, I have to specify that the daemon shares with us the desire to get the photon to come out in that direction, and so. Let me think.
If you're not able to put them in superposition between 0 and 1, then that's not under the control. I mean, that's not under the daemon's control.
The daemon chooses the polarization.
Yeah, I'm not sure if I understand the point. I thought I did, but I now think I was confused. No, if we allow the daemon to choose a superposition, then everything is as in the classical case. So everything is depending on discreteness here.
But say the daemon puts it at L equals 0, won't there be a probability that the photon just goes straight through and isn't
Well, it
reflected?
chooses the polarization of that photon in such a way that it gets reflected by the equation.
What? I think there's something that I need to think about there, but I think at a minimum what I get, and I think this is still enough for me in this case, is that if I know that the daemon is putting all the photons in through that channel, I can't ensure that every photon will come out, but I can ensure that any photon that is reflected has the polarization I want. So I can't ensure that every photon will emerge where I want it to emerge. But what I can ensure is that every photon that does emerge in that direction has the polarization that I want. And I'm pretty sure that's enough for my purposes. Okay, so I'll move on to the right-hand case. Now, again, we control the right-hand polarizer here, but not the output beams. Nature is controlling those. Question is, can we control some property tau r of the input beams? And I've now given it a different name because we'll see in a moment that at least in a straightforward case, it can't be the same property as tau L. And the answer turns out to be yes on two assumptions. One is the discreteness assumption that we just had on the left. So it's the assumption that nature has to put the output photon on one channel or the other. And really the assumption that that's all the ontology there is on nature's side. Again, this is something that could come up in Q&A. If we have something like a bone picture in which the photon comes out on one channel or the other, but there's also a wave function, then that discreteness doesn't hold in that case. So, but again, we can come back to that in discussion. Okay, so that's one assumption, and it plays the same role as it did on the left. The other assumption we need is time symmetry. And this is the assumption that the ontology of the system is time symmetric. And it's this that guarantees that if tau L exists, then tau R must exist, standing in the corresponding relation to the stuff on the right, just as tau L does to the stuff on the left. Now, under those assumptions, it follows, just as it followed in the case of the tau L on the left, it follows that tau r must either be equal to sigma r here or equal to sigma r plus pi on 2. So that, again, we can't fix tau r completely, but we can restrict it to just two possibilities. And again, that means we can depict it like this, and you can see that in this case, as I make changes here on the left, I'm changing some property of the photon before it gets to the polarizer. Okay, but of course, time symmetry is doing a lot of work here in what many people would regard as a standard quantum model. You don't have it. If you think of something like a collapse picture, there's nothing corresponding to tau r in that picture, but by the same token, the picture is not time symmetric. Okay, so that's where the retrocausality is under these assumptions. So we've got three assumptions. We've got the realism one that we had on the earlier slide, we've got the discreteness, and we've got time symmetry. Oh, and just a word about why these two things can't be the same. I mean, if we do have a model in which all of these assumptions are satisfied, so we're committed to tau L, which is partially under the control of the setting here, tau R, which is partially under the setting here, we can choose a setting so that the values of tau L and the values of tau R can't be the same. So is this one. As long as our two settings are not either the same or at 90 degrees to each other, tau L and tau R must be different. I mean, they could conceivably be the same property at different times. I think Ken may be going to say something about models of that kind. And in that case, we'd think of tau L as existing over on this side, as it were, and tau R as existing on that side. But we still need two beables in the model at some point if we're going to have them controlled by different settings, which can be varied independently of one another. Okay, so what this argument shows, I think, is that we have an implication something like this. If we assume realism, we assume time symmetry, and we assume the condition I call discreteness, then the combination of all three commits us to retrocausality, which means that we have a choice. We can reject at least one of these principles on the left, which is really the choice taken by, I mean, if you think of your again, I'm running into the problem that I probably have an unusual audience, but I was going to say, if you think of your favorite quantum model, I was assuming it wasn't a retrocausal model, then it will be a model under which one of those three assumptions fails. I mean, for example, if you're a quantum Bayesian, you'll give up realism. If you like the orthodox picture with collapse, you'll give up time symmetry. Or if you're a Bohmian, you'll give up discreteness. But if you hang on to all three, this argument seems to show that you're committed to retrocausality. And that means, standing back from the choice, it means that we have two options. We can reject one of these assumptions, or we can reject the principle that causation only works forwards. So what are we going to do? Well, let's ask the man in the street for some advice. This is the particular man that I had in mind, or not the particular street. This is Berlin in the early 30s, I think. And really, the Einstein I want to be asking this question to is the Einstein after 1905. And the reason I think that's an interesting question is if you look at what seemed to be Einstein's commitments at that time, it seems clear he's committed to realism. Even more clear that he's committed to time symmetry, because there's the famous exchange with Ritz from 1909, 1910, where Einstein is very clear that he's thinking of time symmetry as being something fundamental at the microscopic level, and is thinking of the apparent asymmetries we see in the world as statistical in nature. And he presumably thinks he's just discovered as what he thought of as his greatest discovery in 1905, that in some deep sense, light is fundamentally discrete. But if that's right, and he wants to hang on to all three of these principles, then he has to give up the principle that we can't affect the past. And that's the sense in which I think that this is an argument which could, in principle, have put retrocausality on the table at a very early stage, and really at a kind of pre-quantum stage. Okay, let's go back to those objections. That I mentioned before, the show me a model objection, and the retrocausality would imply retrosignaling objection, and claim that that would lead to paradoxes. I mean, for example, I could warn my grandmother to avoid her unhappy marriage to my grandfather, that kind of thing. I think it's easy to use the kinds of experiment we've just been considering to provide at least some sort of response to both objections. I mean, a very limited response to the first one, perhaps, but at least perhaps a step in a useful direction. But I think we can say something more substantial about the second one. That is, we can see why the kind of retrocausality that would need to be involved here doesn't lead to retrosignaling. First of all, I think it's helpful to note that we can think of very simple cases in which it seems intuitively clear that we have causality without the possibility of signaling. Here's a simple example. So what we've got in this case, we've got a source of random bits, which are hidden bits. So we've got a coin tossing device behind a screen. The coins land on a conveyor belt and are conveyed along in this direction towards the right. They're behind a screen, so Alice can't see the coins. When each coin arrives, she has the option, still not knowing which way up the coin is sitting, she has the option of flipping it or not flipping it. So for each coin, she makes the choices of to flip or not to flip. And then the coins continue along to the right to Bob. Now, clearly Alice has an influence on this sequence of random bits. Had she made different choices, that sequence would be a different one. Indeed, for each sequence in the bit, it's true individually that had she made a different choice, that bit, the value of that bit would be different. And yet it's also equally clear that she can't use it to signal. I mean, no, from Bob's point of view, it's still a sequence of random bits, and because the bits are hidden from Alice, she can't do anything about that. And if she could see them, then obviously it would be easy for her to use her control to encode a message, but because they're hidden, she can't do that. So in general, causality needn't imply the possibility of signaling. I've already said that. In this case, Alice certainly makes a difference. So there's causality in that intuitive making a different sense, but without the possibility of signaling. Okay, so now let's go back to this is the kind of two polarizer experiment that we were considering in the last section, but it now drawn in terms of a space-time diagram like this. Now, in this kind of experiment, I mentioned this at some point earlier on, if Alice controls the input channel, then she can easily use this experiment to send messages to Bob. Because if she controls the input channel, she can control the polarization here. Bob can detect the polarization, and you've got a signaling device. But in the case we were looking at, where we had a daemon back here making this choice of input channel, now suppose the daemon is just a randomizer. I mean, I've now called the daemon Erotan because the daemon is effectively doing what nature does. So the daemon is like a sort of time reverse version of nature. In the case in which we've got the daemon or a randomizer supplying bits at random on the two channels, then it's just like the case of the random string of coin tosses. Alice makes a difference to the polarization at this stage, But since she can't choose between, say, tau and tau plus 90 degrees, she can't use that. She can't use that influence to signal. And again, this sort of hidden randomness is playing a crucial role there. Okay, now I want to apply that. I mean, so I want to apply that simple observation about this simple time-like experiment to an EPR experiment in order to show that the kind of retrocausality that we need to put in to exploit the Parisian zigzag doesn't allow signaling either. And to do that, I'm going to exploit a simple visual trick. So what I'm going to do is to take this diagram here that we've got on the right-hand side of the slide, and I want you to imagine taking that diagram. Imagine I could cut it out of the screen and then tilt it backwards into the wall, and then I'm going to put a mirror on it. So here's that same diagram tilted backwards. Here's a mirror sitting on it. Sitting on it at the sort of mid-level. This is this red arrow is the kind of axis around which I've tilted it back. Now, in this mirror here, you can see a reflection of this part of the original diagram. And if you look at what you can see above the red line, then what you see looks like the space-time diagram of an ordinary EPR Bell experiment done with two polarizers. And in the mirror, the choices made by this time-reversed Alice, that's Aquila, are making a difference to the polarization of the photon before it reaches this polarizer. I mean, that's just the mirror reflection of what happens down here. This difference, now thought of in the context of this diagram, this EPR space-like diagram, makes exactly the same contribution to the explanation of the correlations between the results here and the results here, as it does to the explanation of the correlation between the results here and the results here. But although this feature, the fact that in the diagram now we now have this element of retrocausality here, it can't be used by Aquila to signal to Bob for exactly the reason that the original pattern of which that we had in the original diagram can't be used by Alice to signal to Bob. After all, if we had something which was a signal up here in the mirror reflection, it would also be a signal from Alice to Bob. Okay, now, of course, as it stands, what we see in the top half of the diagram here is spatially asymmetric, because we see something which has got an influence going from Aquila to Bob, but not an influence going from Bob to Aquila. So it's spatially asymmetric in just the way that the standard picture of the time-like case is time asymmetric. But we can easily fix both of those things by simply giving Bob the same degree of control as Alice, or equivalently as Aquila. And that's exactly the step which was mandated in the original argument by time symmetry. Okay, so in this case, when we're looking at the EPR Bell case, the idea of introducing the zigzag was sort of motivated by the desire to avoid non-locality. In this case, in the last section, it was motivated by the desire to avoid time asymmetry. So we had these sort of two different kinds of motivations, but there's this nice sense in which they're leading to the same place, and it's that sense that I'm trying to convey by as it were, helping myself to the mirror in this diagram. So where does this leave us? I think it leaves us, in effect, with two arguments for the Parisian zigzag, for taking it seriously. One argument comes from Bell's theorem. Bell's theorem is normally formalized something like this: locality plus an assumption which is sometimes called independence, but which amounts to a no retrocausality condition, implies something incompatible with the predictions of quantum mechanics. Or equivalently, quantum mechanics plus this no retrocausality assumption implies non-locality. That is, it implies what Schrödinger called magic. Which means, writing the same equation in a different way, that we could treat Bell's theorem as saying that quantum mechanics plus locality or no magic implies retrocausality. So that's the way of reading Bell's theorem as an argument for retrocausality. As we saw, it's an argument that it's a way of putting it that Bell himself didn't like, but it's there in the logic as a possibility. The new argument, taking realism for granted at the moment, says that quantization plus time symmetry implies retrocausality. So those are two independent arguments, at least I think they're independent, although what they depend on, the crucial quantum bit, is very much the same thing, because of course they depend on the correlations between the discrete outcomes in the kinds of experiments we've been looking at. So it may be that there's some deeper connection that I'm currently missing. And if anyone has thoughts about that, I'd be extremely interested. But as it stands, I think that there are these two independent reasons for taking the possibility of retrocausality seriously. One coming from its relevance to locality, the other coming from time symmetry. Okay, just to finish up then with something which is not associated with Paris, but with Trinity College. This is Dennis Sharma, a very influential physicist here in Trinity, doctoral advisor for a very long list of very distinguished figures. And this is from a little-known paper of his in an obscure collection on determinism, edited by Sidney Hook in the 1950s. And it's something I came across years and years ago and always thought of as something which is in some sense sympathetic to the ideas of retrocausality. It's a very short piece, only about 2 pages. But the basic idea is that Sharma is suggesting that the apparently indeterministic character of quantum theory comes from, as it were, looking at it in a sort of biased way, looking at it in a sort of time asymmetric way. He says the basic way in which quantum mechanics differs from classical mechanics is the following. Our inferences about the future must be expressed in terms of probabilities. This introduction of probability would enable us to make the calculation. With this state of affairs in mind, he says, let us make a new assumption. Let us suppose that in nature systems are deterministic in the sense that we can calculate the system of a time at t if we know enough boundary conditions referring to times other than t. But let us differ from classical mechanics by supposing that nature is so constructed that, roughly speaking, half the boundary conditions must refer to the past and half to the future of the moment t. In other words, we assume that nature is such that mixed boundary conditions, time-symmetric boundary conditions, are always needed. And he goes on to propose that perhaps quantum mechanics is just such a theory. And then to speculate about whether, starting from this point, you could, as it were, come up with some kind of testable consequences by, for example, deriving some expression for the value of Planck's constant, and thus for the difference between the quantum and the classical case. Okay, so I don't think it's exactly retrocausality. so far as I can tell, it's very similar to an idea suggested about 20 years previously in the 1930s by Greta Herrmann, who I think was interested in this sort of time-symmetric causality picture as a way of sort of defending a kind of Kantian deterministic view. But it's certainly somewhere in the same ballpark, in the sense that it's suggesting that our ordinary, rather time-asymmetric picture of quantum mechanics is misleading, and that the underlying picture is much more time-symmetric. Okay, so that's Sharma. That's the Parisian zigzag. You see, it's so famous in Paris that they've got this cafe named after it. And here's a couple of recent pieces, one by me, one by Ken Wharton and my Sydney student Pete Evans, in which you can find some of the material that I've been talking about. Thank you.